I want to begin with what we learned in our last lecture. We started with something that you already know, which is numbers. And you've been using numbers since you were a young child. Even if you didn't know what they were or quite how to use them, you were encountering numbers, and you soon learned how to count and how to quantify using those numbers. But what we also learned was that if you do research, if you collect numbers deliberately, then they're not just numbers, they become data. And what we can do with our data is to organize it. We can organize our data into variables. If I ask everybody, how tall are you? And I get a number from each one of you, I can put those numbers into a column. I now have a variable called height. But if I have multiple variables, I can organize those variables into a data set. So we've gone from numbers to data to variables to a data set, which then leads us to our discussion today. What are we going to do with that data set? And the answer is always the same. We collect data, we compile that data set so that we can ask and answer questions. And those are called research questions. So we're going to ask research questions and we're going to answer those research questions. What does that look like? Well, maybe a little bit like this. I want to answer the research question, what is the best dog toy? Okay, how am I going to do that? Well, I'm going to collect data. Maybe I'll talk to some dogs and I get some information. And I gather those numbers, I organize it into variables, into a data set, and now I can answer that question. However, before I can answer that question, there's something else really important that I must do. I have to be more specific, because this isn't really a research question, this is more of a research interest. The research question is going to require that I get specific. What do I mean by best? I need to be able to tell you precisely, in measurable terms, what I mean when I say what is the best dog toy. So I can think of maybe two directions I could go with that. Maybe I could answer a question about best as which one is most popular. If I ask a group of dogs what dog toy they like the best, what is their favorite toy, whatever is the most popular toy, that one must be the best. Or I could quantify. I could keep track of how long a certain toy lasts before it gets chewed up, its durability. The toys that last the longest, those are the toys that are the best. Now what you'll notice here is I have actually two kinds of variables at play. I have a categorical variable. If I ask what is your favorite dog toy, that's a category. Or I have a quantitative variable. If I ask how long before this toy was chewed up, its number of days before failure, that's a quantitative variable. So I have both a scale and a nominal variable. Both of these are part of what is called operational definition. I must operationally define exactly what I mean when I say something like, what is the best dog toy? Now that I've refined my research question, I collect data. I go out and I survey 50 dogs, and I ask them all the same questions. I ask them questions like, what is your favorite dog toy? I ask them, how many dog toys do you own? I make note of the breed of the dog, retriever, fuzzy dogs, chihuahuas. I make note of the size of the dog, small, medium, or large. And then, as a special thank you for participating, I let the dogs choose a gift, an incentive for participating. They get to choose from among one of 3 toys. And what I'm going to do then is keep track of how long before that gift toy got chewed up, and that goes into my data set as well. So I have a variable for which toy was chosen. I have a variable for days to failure, how many days before the toy was chewed up. And then I have another variable called favorite toy 3, which I can create based upon the favorite toy variable. And what I notice is that some of these toys have things in common. Now, tennis ball is just going to stay as tennis ball, but stuffed monkey and chirpy bird both squeak, so I'm going to call those noisy toys. And the chew toy and the rope bone, those are both chewy toys. So what I've done is I've taken my 5 categories and collapsed them into 3 categories. I gave that variable a new name called favorite toy 3. And then I've recorded the sex of the dog, male or female, and it goes into my final column. What you will notice about all of these variables is these variables are raw data. If I ask you, what is the best dog toy? What is the favorite toy among the dogs? It's really hard to tell. If I ask you, which toys lasted the longest? What was the average number of days to fail? Very difficult to tell. Why is that? Because I have raw data. Scores that are not cleaned, summarized, or displayed in graphs are called raw. They're not ready for public consumption. They're not ready to be consumed. They're not ready to be delivered to someone else who can read about them and understand them. The point of having raw data is kind of like having raw food. Before it is served, we have to prepare it. Now, I don't know, maybe you're someone who likes raw meat. You like steak tartare, and lots of people like raw vegetables. That's fine. Even then, if you go to a restaurant and order something that's raw, oysters or anything, they're still going to prepare it. Not just going to slap a steak on your plate and hand you a carrot. They're going to prepare this. That's what we have to do. When we have raw data, we have to prepare that data so that it is easier to consume. It is easier to answer the question that I've asked about what is the best dog toy. So how am I going to get these raw data ready to serve? And the answer is descriptive statistics, which are just what they sound like. They are statistics that we use to describe data. In the same way that I could describe a friend as being friendly or tall or handsome or smart, I can describe my data points. But I'm not going to describe the data as being good looking. I'm going to describe the data based upon the qualities of the data. There are 2 ways that I would go about describing my data points. The first is to put them into numbers. And those numbers often work well in tables. That's where we're going to focus a lot today because we're talking about frequency tables. In this example, I have categorical data about what is your favorite dog toy. And I have listed the number of dogs that have chosen each one of these types of toys, along with the percentage of dogs. This is a numerical summary. Another very common way that we will see our raw data served up is through a picture, a graph, a chart of some kind. In this case, I've created a bar chart. So I can see that 12 dogs chose tennis ball as their favorite toy, which corresponds to what I can see numerically over in my table. The 2 ways that we will be displaying data would be numbers and pictures, or tables and graphs. Here is my raw data. In this form, there's not much I can do with it. But when I prepare it properly, now I can ask, what's the best dog toy? And you say, what do you mean? And I say, what was the most popular dog toy? And you say, oh, I can tell you that really easily. That was tennis ball. In this Pareto bar chart, I could even ask you what was the 3rd most popular toy. And you can find stuffed monkey very readily as well, because I have properly cleaned and prepared my data to serve it up. So now I can ask and answer those research questions. So now we're really ready to drill down into what it would mean to describe data. If I give you raw data and ask you to describe it, you're probably going to have 2 questions about each variable. The first would be, how many scores do we have? So for instance, with this table, I have 5 different groupings, and I have 50 dogs. So how many scores do I have, and how often does each score occur? I can see here that 10 of the dogs chose stuffed monkey, which actually represents 20% of the dogs in my data set. We're going to be using 2 letters, N and F, to represent the answers to how many and how often. The how many question is that N. N is our sample size. It's telling us how many scores, how many participants, how many values in my data set. I surveyed 50 dogs, so if I ask you what is the sample size, your answer would be N equals 50. If I have a bag full of poker chips, and I tell you that there are 24 poker chips in this bag, what is the sample size? N equals 24. Lowercase n is a subset or a subgroup. If you know that there are 16 dogs out of the 50 who were Chihuahuas, then the lowercase n representing Chihuahuas would be 16. My uppercase n is always going to stay constant at 50, but the lowercase n will change depending upon what part of the data set I ask you about. Any subgroup or subcategory would be represented with that lowercase n. The frequency is how often a particular score occurs. If 12 dogs chose tennis balls, the frequency of choosing tennis ball would be F equals 12. We still have a larger N of 50. In that bag of poker chips, if 14 are red, 7 are blue, and 3 are green, out of our total of 24, the lowercase n for red would be 14, the lowercase n for blue would be 7, lowercase n for green would be 3. So I'm able to answer how many and how much. That would be an example with some categorical data. So let's continue talking about categorical data and how we calculate frequency when we have data at the nominal or the ordinal level. This is an example of a frequency distribution, which is defined as an organized summary of how the values are distributed across categories or ranges. What are the categories? Well, we see those listed as stuffed monkey and rope bone, etc. Right? And the values have been organized with the number of dogs choosing that particular category and the percentage represented. This is how we're going to represent categorical variables. We will most commonly represent the n, the small or the lowercase n of that particular subgroup, as well as the percentage that represents in our total data set. We will make these decisions based on our level of measurement. So I'm talking about categorical variables. I'm going to be reporting the frequency and the n value in a table. If I draw a picture, it'll be a bar graph. On the other hand, when I have continuous data, scale level data, I'm still going to report the frequency and the n value, but I'll also include the cumulative frequency, which we're going to come to here in just a little bit. And when I create a picture of my scale level data, that's most likely going to be a histogram. Regardless of what I am organizing, I want to put it into a table so that it's easier for you to understand exactly what is contained within my data set. So a frequency table is going to display the categories of data. Often you will see either the X value, which would be the first category, or in the case that we know a variable name like favorite toy, I might just substitute favorite toy for the X value, and you would still see the subcategories underneath that. And that's going to be followed by the number of times each data point occurs, which would be the frequency value. So 12 dogs chose this particular toy. Now there are 2 things that must be true for our frequency table to be valid. Number 1 is the frequencies must be mutually exclusive. This means each observation can only be counted 1 time. If we have 50 dogs, we should have only 50 values. They cannot fit into more than one category. They can't choose 2 toys or have 2 favorite toys. They must fit into only one category. And the second quality is it's collectively exhaustive. Every observation in my data set must go somewhere. So once we have that, we can then add up the total number, we can calculate frequency, we can put that into a table. This is what a categorical frequency table might look like. So note that I have the variable name, I just called it toy, and here's the 5 categories. Here's the frequency for each of those categories. You'll notice now they've been organized from largest to smallest. Here's my relative frequency, we're going to come to that, and my percent frequency. This would be a typical APA-style formatted categorical frequency table. Let's talk through what goes into each of those columns. The first column is going to be the simple frequency. Simple frequency, the number of times that any category appears in the data set. If our category is tennis ball, 12 dogs chose tennis ball as their favorite. The frequency would be 12 for tennis ball for this data set. Because we have all of these categories that must be accounted for, then what you will know is that if you add up all of those frequencies in that column, they must add up to n. If there's 5 toys, you add up the frequency in each of those 5 categories, they must add up to the total number of categories. If they don't, something is very wrong. You need to go back and check your data set and confirm, why does the sum of my frequencies not equal n? There was a mistake somewhere. Sum of the frequencies should always equal n. Now here's a note about frequencies. Be wary when you have a very small sample size. Now remember, percentages, right, would be like a percent would be per 100. But like in this case, because there's only 50 dogs, each dog would be like 2% worth. If you have 12 people in a data set, each one can represent much more than 1%. And that means that those percentages are not going to be easily comparable between data sets. So be aware of the sample size when you're interpreting these frequencies, especially when interpreting the percent frequency. Simple frequency is the number of times each category occurs. The proportion of times that a category appears in the data set is called your relative frequency. Relative frequency allows me to do some comparisons. If I simply tell you that 12 dogs chose tennis ball, that's not very useful if you're trying to extrapolate that from your sample to the population. But if I give you a relative frequency, like of a 0.20, well now you can make some comparisons. So you can compare the relative frequency, which is the number between 0 and 1. Can't be less than 0, can't be greater than 1. It will be presented as a decimal. You can compare that value and tell which group has more in it. So a 0.20 relative frequency in this data set would be proportional to 1 in a different data set. The problem is, this is not very intuitive. It's difficult to understand these kind of relative frequencies, and that's why you rarely, if ever, see them reported. Instead, what we're going to do is clean up the relative frequency by multiplying by 100 and converting it to a percentage. That is the statistic of choice if we're talking about the relative frequency of a score occurring in a data set. We'll convert it to a percentage. Instead of saying 9 dogs chose rope bone or 0.18%, 0.18 relative frequency, I'm going to say 18% of the dogs chose rope bone. And if you've replicated this with a data set of your own where you've also surveyed a number of dogs, you can say, well, 18% chose that in my group as well, or 20% chose it. I can compare now between data sets using that percentage point. So this is going to be our best choice for general audiences. And again, we want to be careful whenever there is a small sample size. Those proportions and percentages can be somewhat misleading. So that is how we're going to represent frequency with our categorical variables. Let's talk now about how we would use frequency with continuous or quantitative data. Here's your raw data. Number of days to fail. What's the average? What's the frequency? How many dogs took 12 days to chew up their toy? You see the problem. The raw data is far too difficult to interpret. We've got to clean this up. So here's one way I could clean it up. I could simply put these days to fail number in order from 1 to 20 and give you the frequency for each one of them. The problem with this kind of table, however, is that there are so many values that it still makes it difficult to interpret. When we use continuous or quantitative data with this type of frequency table, what we're going to do is bin the data, B-I-N. We're going to create bins for the data points that would look like this. I have my days to fail, 1 to 4. Any value between 1 and 4 goes into this bin as a frequency of 6. Days 5 to 8 has a frequency of 19. So now I've created a much more manageable frequency table by creating bins with my data. Okay? So let's look at the categories that we have here. The categories are going to be listed in your first column, which could be the same as your variable name. And as we saw with our categorical data, these bins must be mutually exclusive and collectively exhaustive. This is an error that you will sometimes, maybe often see. You want to be aware of, especially when people do things like age banding. Part of the problem is that sometimes Excel will do this by default. So just be aware of this happening. Look at my categories and tell me what's wrong here. I have categories 10 to 20, 20 to 30, 30 to 40. The problem, where would the value of 20 go? Do you see how it could fit into two categories? This is what I mean by mutually exclusive. We want to structure the bins. So in this case, maybe it runs 10 to 19, 20 to 29, 30 to 39, so that any score can only fit into one of those categories. And collectively exhaustive, all of the data points in my data set must go into one of these bins. Now, creating bins is a bit of an art and a science. There's no hard and fast rules. There's a lot of times where you will create a frequency table from your data set and then look at it and think, it doesn't look right, and you'll adjust for it. There's nothing at all wrong with that. Your goal is always to present your data honestly and clearly, and if adjusting the size of the bins is required to do that, then that's what we will do. Now, there are some guidelines that we'll want to follow when we are creating those bins. First, the width of each bin should be equal. I see sometimes when researchers bring me data with age groupings, especially if they're starting with, let's say, college age, but they're running through mid-40s. And so they might put 18 to 24 into one category, and then 25 to 34, and then 35 to 44. Those are not the same size bins. So regardless, you want to be sure that the bin sizes are the same. You have to have enough bins to show the variability in your data, but not too many bins that you end up with empty bins somewhere within that bin range. So a good rule of thumb is you're creating bins is going to be somewhere between 5 and 20. If you have a larger data set, you're going to need more bins. Smaller data set, fewer bins. And if you're looking for a formula that will guide your choices, if you take the largest minus the smallest value, divide by the number of bins, that is going to be your bin width. So let me describe what I mean by bin width. I want you to look at this bar chart, and you'll notice a couple of things. One is the bar itself is centered over the score. I have scores running from 3, 4, 5, 6, but the bar for 5 is over the 5, which means that the width of the bar extends in both directions on either side. And that is for a reason. Because when you are using values that have decimals, we have to round. If my data goes to 2 decimals, but I'm creating categories of 4, 5, 6, 7, that means some decimal values, some larger values of 4 are going to round up. And some smaller values of 5 are going to round down. My bar is representing the values that are actually contained within that bar, even though it is centered over an integer value of 5. These are called my bin limits. This is what is actually included in the bar that is represented in that bar graph. The lower limit would be the smallest possible data point in the bin, the one that would round up. The upper limit is the largest possible data point in the bin, the one that would round down, creating this range into which all of my data points can fall. When we look at our categorical data for how many dog toys lasted 1 to 5 days, you're going to see some frequency values that are the same as what we covered with categorical values. So for instance, we create a bin of 1 to 5 days, we can get a simple frequency, which in this case would be 10. The relative frequency, because it's out of 50, would be a 0.20, which is a little hard to interpret. Let's make that a percentage. 20% of the toys lasted 1 to 5 days. Now those 3 are the same as what we talked about with categorical data. But there's one other form of frequency that I need to tell you about that we use only with scale level or quantitative data, and that is called the cumulative frequency. Now the word cumulative means to accumulate. This means that we are counting all of the scores at or below a particular score. In this example, where I have, this is representing like an outbreak of some disease, we can see there's an initial large increase, and then it drops off and it's low, but then there's a smaller outbreak that follows. The cumulative frequency line over here is representing an increasing number of cases. When the cases drop off, it flatlines, and then it increases again. Notice that for my first row, how many dogs own 1 toy, 2 dogs, or 4%. The cumulative percent for my first row is going to be exactly the same as the percentage. It's 4%. How many dogs own 2 toys? Well, there were 3 of those, or 6%. The cumulative percent is now going to be the original percentage plus the next one. So for instance, I'm going to add 4 and 6 and get 10%. And I could just keep working my way down. There were 6 dogs who owned 3 toys, 12%. If I had 12 plus 6 plus 4, that would be 22%. What this allows me to do is to answer questions about how many dogs owned at least this amount of toys, or owned this number of toys or fewer. If I ask you, what percentage of dogs owned 8 or fewer toys, so 8 or less, you could look at the 8 row, you could say 76% of dogs owned 8 or fewer toys. And you could do some math with that. How many owned 9 or more? You can just do the subtraction on that, come up with the value for that as well. So now I am able to look at ranges within my data set, and that's where the cumulative portion comes in. So when you interpret cumulative frequency, there's an important thing to keep in mind. Because it's accumulating, it can never decrease. So here's what it would look like. When you are considering cases where the number of cases is increasing, so here's my increasing cases, you're going to see the cumulative frequency line curving upward, concave upward. When the cases are occurring at a constant level, so the same every week, then we still have an upward slope, but it's going to be more like a 45-degree line. Okay. So when the cases drop off, what we will see is a decrease in the number of cases being added, and eventually that will become a flat line. When there's no new cases being added, the line doesn't decrease, it simply stays flat. So once a certain number of events have occurred, we can't have them unoccur. No new cases is a flat line. And this is what our frequency table might look like. You can see I've created bins for the number of days. There's my simple frequency, my relative frequency, which I've converted to a percentage. Here's my cumulative frequency. So for instance, 10 plus 23 becomes 33, and the cumulative frequency percentage. This is a properly formatted table, although there's probably more information in here than I would actually use. I would probably report the frequency and the percent frequency, perhaps the cumulative frequency percent. I'd leave out the relative frequency. So far, I've been talking about a single variable, one variable at a time. But we can also look at frequencies as they occur when we consider two variables, or a bivariate understanding of the data. The way that we're going to visualize categorical variables when we have more than one is called a cross-tabulation. We will cross them in a table. Cross-tabulation, a crossed table. Now this technique will then allow us to answer more complex research questions. So remember, the whole point of research is to ask and answer questions. Our questions become more complex when we introduce multiple variables. So for instance, I could answer questions like, does dog breed influence which toy is chosen? Are certain types of dogs more likely to choose that hedgehog? Are some types of dogs more likely to destroy toys faster than others? Are there certain breeds that are more likely to destroy their toys more quickly or less quickly? Or I can answer questions like, is toy durability related to dog size? Do larger dogs chew up their toys faster than smaller dogs? Or is it the other way around? I can answer more complex questions by introducing more variables. My cross-tabulation is a joint frequency of two tables. Because it is a table, it will have rows and columns. I'm going to use categorical data. So I'm going to put one categorical variable in a row. In this case, it will be dog breed. And I'll put the other categorical variable in a column. In this case, toy chosen. And in each of the cells of that table, I'll put either a frequency or a percentage so that you'll have that breed by toy combination, which will then allow you to answer some question about the relationship between a breed and a particular toy. This is what that table might look like. So I have breed of dog listed in this column. I have toy chosen listed across this top row. And if I ask you how many fuzzy dogs chose a hedgehog as their gift toy, you know that would be 4. Or how many retrievers chose lamb chop? You can see that would be 5. But you can also start to see patterns as they emerge within this table. Is there a preference for one type of toy among Chihuahuas? We see that hedgehog was most popular and lamb chop least so, versus with retrievers, it's pretty much the same all the way across. They didn't really seem to have much of a preference. Now I'm starting to see patterns. I'm starting to see how these variables work together. These are just the raw numbers, but they would be pretty easy to convert to percentages. And now you could answer questions like what percentage of fuzzy dogs chose, or what percentage of fuzzy dogs their toys lasted for a certain amount of time. So here I've switched from my categorical data to the binned data with the number of days until the toy was chewed up. So I see, for instance, for bins 1 through 5, what percentage of Chihuahuas chewed up their toy in the first 5 days? 56.3%. How about retrievers? I see that none of them chewed up the toy in the first 5 days. Most of them kept their toy from 11 to 15 to 16. 75% of the dogs kept them more than 10 days. I can look at those patterns. I can start making some generalizations about types of dogs and the likelihood of a toy to be destroyed based upon breed. Now I'm getting to more complex questions that I can ask and answer. So I started off the lecture with this research question: what is the best dog toy? We answered that by doing data collection. We surveyed a number of dogs and we asked them very specific questions, each dog getting the same question. We meticulously recorded those answers and we organized them into this data set. So now I can answer, what is the best dog toy? If I'm talking about popularity, I can say 24% of the dogs chose tennis ball. It was the most popular toy choice. If I'm talking about durability, I can say that 8% of the toys lasted for 16 to 20 days, which might mean that the toys aren't very durable. However, once I did the cross-tabulation, I discovered there's probably a different predictor. It's not just toy durability. Breed plays an important role. There are some breeds that are more likely to chew up their toy, so maybe I'm not talking about durability. Maybe I'm talking about another predictor variable. So by breed, Chihuahuas kept their toys the shortest, they chewed them up the quickest. Retrievers kept their toys the longest. So what we've been talking about is frequency. Frequency organizes our data set. What we're going to move to next is to visualize that data set. I want to see what is in those data points. So I'm going to use both categorical and continuous variables with different types of charts and graphs to graphically depict what's going on. And that's going to be our topic for next time. So I want to thank you for being here. And I'll be happy to stick around, answer any questions that you have. But for now, we're going to wrap up, and I'll see you next time.